Hello students, welcome to Mechanical Design. In today's lecture, we're going to review the Cartesian coordinate system, ideas of stress as a tensor, and we're also going to learn how to find the principal stresses as well as their directions. So let's go ahead and get started with the Cartesian stress components. A Cartesian coordinate system is defined by three orthogonal surfaces that act at a point within a body. When we think of a Cartesian coordinate system, we can think of the coordinate systems we know. The classic coordinate system consisting of x, y, and z axes. Now in general, when we think of stress in Cartesian components, stress can be described as having both normal components as well as shear stress components, right? And our shear stress components may actually act along more than one axis, so they can act in two axes. So let's start with one surface. Let's draw a Cartesian coordinate system, so x and y and z. And then let's draw a surface, a 2D surface, which has x as its normal. On this surface, we can draw our normal stress, which is a stress that is normal to the surface, sigma xx. But we can also draw shear stresses that act parallel to the surface. And one option here is if we are directing an arrow in the y direction across the x surface, we get a shear stress tau xy. We can also direct a stress in the z direction, right, across surface x. And we end up with a shear stress tau x and z. So when we consider the indices that we're placing, the first and the second one, for each of these types of stress, we can define that our stress components, sigma, have the first index indicating what surface that the stress is acting on, and the second index, j, indicating the direction that stress is acting. So we've done our little example for 2D. Now let's move this into 3D, where we actually build all of our surfaces that create a 3D element. And when we do that, we'll find that we have quite a complicated state of stress in a single element, right? So we take that original surface we had, and we add additional surfaces. So a surface here with a plus y normal, and a surface here with a plus z normal, and then we can identify these the stresses, the normal stresses, sigma x, sigma y, and sigma z. And of course we can put xx, yy, zz. And then also our shear stresses, tau xy, tau xz, tau yx, tau yz, and then tau zy and tau zx. Now it's important to note that in the drawing that we have here, that what's missing are the negative surfaces, the back surfaces, the ones we can't see. So the surface that's on the bottom of this element, this one here, we can't, we're not drawing those stresses. This back surface here, and then the back surface there. But in order to maintain equilibrium, it is required that we have stresses, both normal and shear, acting on those negative surfaces. And when we consider that, we can then build a stress tensor which describes the state of stress within this body, where our stress tensor sigma is indicated as a tensor by a double line under the symbol, which indicates a tensor. And it's represented as a matrix where our rows indicate the surfaces and our directions are our columns, right? So if we look at our first term here, it's acting on surface X and it's acting in direction X. If we take the adjacent term, it's acting on surface X and in the direction Y, right? And we'll note here that if we look at the indices of the off-diagonal terms, so if we look at the indices and compare them of the off-diagonal terms, in all cases, we switch our indices. We're switching the direction and the surface that these shear stresses are acting on. And so with this knowledge, and with knowledge that we must maintain equilibrium, we'll find that these terms are identical to each other. The magnitude of these values are identical. Which is a great relationship that greatly simplifies the way that we deal with stress. Because instead of having 9 independent terms, the stress tensor actually regresses to 6 terms. So there's 6 unknowns that we would have to deal with. 6 components that we would need to find, right? And this is for a 3D element. Now often, and let's type this in here as we go. Often we use the 2D element to solve engineering problems. So often we can take a problem that we have that might be in 3 dimensions and simplify it into some kind of 2D surface, right? And we create our free body diagrams. When we do that, then we can simply define a Cartesian coordinate system with X and Y, where our Z axis is coming out of the page, and we can simplify our stress tensor. There are double lines under it indicating it's a tensor, and simplify it into a 2x2. We have our normal stresses, sigma x and sigma y, and then we have our shear stresses, tau xy and tau yx. And where we remember that tau xy must equal tau yx for equilibrium. For equilibrium to exist, this must be true, right? And so now we've got this concept of stress as a tensor and stress happening on the surfaces of elements. And we can see that it's quite complicated, right? Now we'll move into the idea of Mohr's circle. And we're going to do Mohr's circle for plane stress. So let's start with, say we take a 2D stress element and we section that element at an angle theta. And that angle theta is relative to the positive x-axis. So if we do that, we take our 2D stress element and we section that element relative to our positive x-axis. We're going to expose a new surface. we expose a new surface that has an internal normal and shear stress. These stresses exist to maintain equilibrium of our element. So we remember, we must always remember that if we have some part, some full part that we say is in equilibrium, then we can section and cut it into any pieces at any angle and always maintain equilibrium by exposing the internal normal and shear stresses or the internal normal and shear forces, right? And so we expose these normal and shear values, the normal sigma and shear values at that angle. Now we can describe the normal and shear stresses as a function of the angle theta. It's a function of that angle theta. And let's highlight these appropriately. Normal and shear, a function of the angle theta. Or actually, the angle we have here is phi. So let's change this from theta to phi. And let's underline that with the color phi and tell you that, hey, this is phi here, right? So, so since we're cutting at an arbitrary angle phi, we can then go ahead and describe the normal and shear stresses as a function of that variable phi. And let's do that. So our normal stress on that surface is going to be equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine of 2 phi, where that 2 and phi is inside of the cosine brackets, plus tau xy sine of 2 phi. And all we're doing here is we're simply applying the idea of equilibrium to this particular problem, to this actual diagram here. What is needed, what balance of sigma x, sigma y, and tau xy is needed for this normal stress that we have on this exposed surface. Similarly, the shear stress on the surface, let's zoom in a little bit here, is equal to negative sigma x minus sigma y divided by 2 sine of 2 phi plus tau xy, the cosine of 2 phi. So taking these two equations, we're able to cut a 2D element. So we can cut a 2D element at any angle and find the values of the normal and shear stress that are exposed on that surface by using these two equations, right? And of course, we could derive these equations if we were asked to. If we were asked to derive them, we could find them. But luckily, they're given to us, and we're going to use them. We're going to exploit these two equations to explore different values of normal and shear stress at different angles of phi. So let's do that. So if we differentiate the normal stress equation and set it equal to 0, we can solve for the cutting angle phi P, it's called phi P, where normal stress is maximized. So if we just do a little bit of calculus, we take our normal stress equation, this one here, and we differentiate the equation and set it equal to 0, we can solve for our cutting angle. We can solve for the angle that leads to a maximum, the largest value of normal stress. And we'll find that the equation that describes that is, let's zoom in here, tan 2 phi P, so that's that cutting angle, is equal to 2 tau xy sigma x minus sigma y, where this is the cutting angle where the normal stress is maximized. And when we exercise this equation, so let's move it over, when exercised, we find there exist two angles where the normal stress is maximized. So there actually exists a phi P1 and a phi P2, right? So there's actually two orientations where this is maximized. Now, coincidentally, at these orientations, the shear stress on the cutting plane is equal to 0. So we actually found that if we can find those two angles, if we can solve this equation and find those two angles, at both of those orientations, there exists no shear stress on our cutting plane. We've actually eliminated, which is really cool. And so in essence, we've found the principal directions within this body. So for 2D problems, let's review this. For 2D problems, there are two angles, and the angles phi P1 and phi P2 are called principal directions. And associated with each of these angles, we will find a value of normal stress, sigma 1 and sigma 2. And these stresses are called principal stresses. And shear stress does not exist at these orientations. So these are the, for 2D problems, these are the three rules that we found as it relates to that phi P, to the phi P's, right? And then we can also find, through manipulation, there exists a relationship between phi P1 and phi P2, where phi P2 is equal to phi P1 plus or minus 90 degrees, and where sigma 1 is greater than sigma 2. So it's larger than sigma 2. Okay, so we've found our principal stress directions and values and the relationship between them, right? So how about we go ahead and title this here, Principal Stresses and Directions. Okay, so we've differentiated. Let's remind ourselves, we differentiated this first equation, set it equal to 0, and we were able to find these principal stresses and directions. Well, what about this second equation, this shear stress equation? Couldn't we do the same thing? And if we did do the same thing, what would we find? What would we actually be finding if we did that? Let's talk about it. Let's attempt it. So let's say, similar to the previous example, let's differentiate the shear stress equation and set it equal to 0. We can solve for the cutting angles phi s, where the shear stress is extreme! Exclamation, all right? So we can actually find, so we can actually go ahead and do that. We can differentiate the shear stress equation, set it equal to 0, and solve for some cutting angles phi s, where we can say our shear stress is extreme values of shear stress. So when we do that, we'll find the equation tan 2 phi s is equal to negative sigma x minus sigma y divided by 2 tau xy, where if we take the values of stress we know and plug them into this equation, we can find the angle phi s. And when we do that, we'll again find that when exercised, there exist two angles, and those angles we can call phi s1 and phi s2. So we can find two angles where our shear stress is extreme. Now, interestingly, when we perform this operation, unlike the previous example, normal stress exists, and it exists at a value of sigma x plus sigma y divided by 2. So it exists almost as like an average stress, or average of the normal stresses, right? Okay. And let's circle that one as well, because it's important. Now, you know, we've got our phi s1 and our phi s2. What are those called? What do we want to call those? Those are called the extreme value shear stress directions, right? And associated with those, if we were to evaluate each of those, so take those angles and plug them back into our equations for normal and shear stress, we'll find a tau 1 and a tau 2 which are called the extreme value shear stresses, right? So each of those is associated with the angles that we find with phi S1 and phi S2. Now, an important thing for us to note also is that there are two relationships that exist. One of the relationships is that phi S2 is equal to phi S1 plus or minus 90 degrees. So similar to the previous example there, there's a relationship, 90 degrees relationship, plus or minus between the angles. But more importantly, there exists a relationship between our principal directions and our extreme value shear stress directions. So let's note, very importantly, let's note that phi S is equal to phi P plus or minus 45 degrees. So there is a relationship between the principal stresses and their directions and the extreme value shear stresses and their directions, right? Oh, that's great. Let me do that. Let me use the bold line. There we go. When introducing new concepts here. Okay. So now that we've taken these equations, we've evaluated them, we've come up with this set of equations that help us to define principal stresses and directions. Let's do a little bit of work. And if we do a little bit of work, we can actually find an equation that describes our principal stresses and our extreme value shears. So we can just plug them in directly and solve for them. So we do that when we do that. And let me type these in. Waste my time. There we go. Principal stresses. And we'll find the principal stresses sigma 1 and sigma 2 are equal to sigma x plus sigma y divided by 2 plus or minus the square root of sigma x minus sigma y divided by 2 squared plus tau xy squared, right? So we can actually solve them to the point that the angles, the phi p 1 and 2, don't actually appear in the solution, which is great. It's very useful. We can do the same thing for our extreme value shear. You'll find tau 1 and tau 2 is equal to the second term of our principal stresses. So it's equal to plus or minus the square root of sigma x minus sigma y divided by 2 squared plus tau xy squared. So this is a very beautiful relationship, because then we can say that, hey, this second term, this gives us tau 1 and tau 2. So really, if we just remember this first equation for principal stresses, we can very easily obtain our extreme value shear stresses. So now that we've, identified these important values of stress, both the normal stresses and orientations and the shear values, now we need to figure out how would we plot the relationship between these stresses. How would we plot the different normal and shear stresses that could be generated when we change our angle theta, our angle phi, right? And to do that, we'll actually introduce this idea of Mohr's circle. Now, this is something that you should remember. You remember Mohr's circle from mechanics of materials. Well, we're going to use it here in mechanical design, right? Now, probably the most important thing for us to look at before we do Mohr's circle, before we see it, is to understand the sign convention for Mohr's circle. It's very important for us to try to understand the sign convention. How do we, what do we say is a positive direction or a negative direction? What's a positive shear stress versus a negative shear stress? And where do we start? How do we start? Okay. Let's consider a 2D element and examine the positive x surface or line of that element, right? So if we were to draw a 2D element, and we have the positive x-axis, and here our positive y-axis, then let's look at this line, the positive x line, or we could call it a surface, but it's 2D, so we'll call it a line, right? And this edge, this line in our element will help us to define what is considered positive or negative shear stress within our body. So let's just say that this line will help us to determine positive or negative shear stress in our body. Will also help us to determine how to plot the shear stress on Mohr's circle. So it has two functions. What is the shear stress? And then how do we plot it on Mohr's circle? Now let me get a new sheet here. Let me add a sheet. So that we can explore this further before we get into Mohr's circle. So let's draw a stress element. Let's draw the shear stresses on it, and then let's try to determine, what is the value of shear, or what is the sense of the shear? Is it positive or negative? And then also let's say, well, how will we plot our Mohr's circle? So let's copy that element we've already drawn. And let's draw shear stresses around that element. So say we have shear stress that goes down on our positive x-axis. Well, this shear stress has the tendency, if we just have that if we only have that arrow on this one edge, has a tendency to cause what type of rotation? It's going to cause a clockwise sense of rotation, right? So let's note that. Sense of rotation, right? Now, if we want to maintain equilibrium, then we know that, hey, we need something to balance out the forces in the y direction. So we need to put a shear stress on this other surface. And then also, in terms of momentum, right? If z is coming out of the page, well, these two shear stresses create a kind of couple moment. So if we want to counteract that, we're going to need shear stress, another couple moment, with equal and opposite values in order to balance this system. So we have a clockwise sense of rotation on that positive x line, and the sense of skew that we get of this body is counterclockwise. So the actual shear stress is negative. When we see this configuration, the actual shear stress value is a negative sign. And we get a clockwise sense of rotation on that outer surface. Now when we plot Mohr's circle, we are going to plot above the x-axis. So our value of shear stress is negative. We have a clockwise sense of rotation on our positive x line. And when we plot Mohr's circle, we plot above the x-axis. So if we have an element and our shear stresses look like this in our equations, we're going to use negative. And yet when we plot Mohr's circle, we're going to plot our shear stresses above the x-axis. If we're above the x-axis, that seems like it's positive, right? But it's not. Okay? So let's move this up. Oh, well, we still got more room here. All right. Let's move this way up. And let's just call this negative shear stress element. All right. Now let's draw the positive shear stress element. And let's, kind of learn about what are the little tricks with that. Well, let's again copy this element. And let's delete these pre-existing values here. And let's start fresh. So in our previous example, we started with our plus x line, and we drew the arrow downwards. Here, let's do the opposite. Draw our arrow upwards. We don't need a plus sign here, but draw our arrows upwards, tau xy. Now, in order to maintain a balance on the negative x line, our arrow needs to go downwards. And in fact, before we even draw this, let's consider what sense of rotation does this single shear produce in our element. And the sense we get is a counter-clockwise sense of rotation on that positive x. Right? Now let's go ahead and place our shear stresses on everywhere that they need to go. So for equilibrium in the y direction, and then for equilibrium of the moments of this element. And again, these values must be equal and opposite in order to balance each other out, or well, not equal and opposite, but opposite directions, right? In terms of the moment. So these would generate counterclockwise, these two, while these would generate clockwise, balancing each other out in terms of the moment, right? Now, if we look at this body, the skew that we would get due to these shears is actually clockwise skew. And that clockwise skew will mean that our shear stress is positive in this element. And this positive sign would be used in our equations. So when we are given an element and the arrows look in this way, where it's skewed clockwise, we are going to use positive values for shear in the equations that we're going to use. But when we plot Mohr's circle, we are going to plot these shear stresses below the x-axis. Very important, right? We're going to actually plot them below the x-axis. So ideally, you should, once you've become very familiar with these types of problems, should be able to identify these three concepts. Identify that positive x line, what sense do we get, identify what sense of skew we get, so should we have a shear stress that's negative or positive, and then lastly, from there figure out should we be plotting above or below the x-axis in Mohr's circle. So now let's go ahead and let's look at Mohr's circle. Okay. And again, we're remembering all of the hard work that we did in mechanics of materials. And simply reapplying that here, right? Okay. Looks like our notes have frozen. It's like the notes have frozen. So I guess this is probably a good place for us to stop for today. In our next class, we will go over the concepts, each of the concepts and locations of Mohr's circle, building it up from the ground up, and then we will actually do an example of finding our principal stresses, finding our shear stresses, and then drawing Mohr's circle from those concepts. So that is the end of class for today, and I'll see you next time.